So in this video, I'm going to be going over and or summarizing how to solve motion problems and relative velocity problems. So if you've seen some of my previous videos, I have already solved some motion problems and some relative velocity problems. In this video, I'm not necessarily going to be going over a specific problem. It's more like it's just a summary of all those previous videos, okay? And so I'm going to be going over three things: how to solve motion problems, simple motion problems, more complicated motion problems, and relative velocity problems. Okay. So in this first one, simple problems, how to solve them. Now, obviously, you could just open up your physics textbook, right, and it says, oh, if you have this scenario, use this equation. In a different scenario, use another equation. And even more, even in another situation, use like another equation. Now, you could do that, but the problem with that is you have to memorize all these equations. Like I have 1,000 equations I have to remember. What I'm showing you here is that you don't actually have to use those equations. I've solved in the textbook that I'm using I solved all the problems in the back of the book, and I didn't use any of the equations that they gave me. I sort of solved them from like first principles. Basically, just using pure mathematics to solve the problems instead of just being given the problem. Instead of being given the function or given the equation, you can kind of just come up with it on your own. And therefore, I think it makes more intuitive sense. If someone just gives you an equation, it's like, what is this thing doing? But if you can kind of just solve it, on your own without using those pre-given equations, it might make more sense. Okay, so what I like to do, obviously, you have to read the problem. Number two, I like to sketch out a problem. Number three, draw like different graphs, like acceleration versus time, velocity versus time, the position versus time, and create these graphs not only for all the components like x, y, and z, or axes that the object may be moving in, but for all the objects. Oh, I got a dog and a cat and an airplane. So if you have three objects and let's say they're moving in, it's just in a plane, an XY plane. Well, you have 3 times 2. You'd have to create, which is obviously 6. You'd have to create 6 graphs. Okay. Now, for some of you thinking out there, well, that's a lot of graphs. I would just like use an equation. And that's fine. Like, I'm not saying don't use a pre-given equation, but this is just a way for you to solve these problems without having to use any equations, right? All you need is just some paper and your brain, basically. Okay, so draw out the graphs, and then once you have those out, then use a combination of algebra, trigonometry, calculus, to try to derive the missing functions of motion. And then I have a note in here. Be careful when you're integrating, as when you integrate a function, you're going to miss the initial conditions. It won't be in the integration itself, right? It won't come out of the math. You'll just have to know what the initial conditions are. So just be sure when you're integrating that you find out what your initial conditions are and then add that to your function. And then you're going to have a bunch of functions, right? And then you're going to have to set one function equal to another one, possibly, or solve a system of equations. You're going to have to do that to come up with your actual answer. So, to show this, once again, I'm not going to go over a specific problem. It's just generally what would you do. So you read the problem, and then you kind of sketch it out. Like, oh, there's a person here, and maybe they're throwing a ball, and my origin is here, and I don't know, there's like a brick wall or something, and it has to go over the brick wall, and maybe the ball's going to land here, and that maybe you write down, oh, like the initial velocity of the ball is, I don't know, like 3 meters per second or something like that, and you have to remember. Hold on just one second. Let me turn this off. And you have to remember, oh, yeah, the ball is also being affected by gravity. So you say, well, gravity is 9.8 meters per second squared, right? And just write down everything that you know, right? And so you say, okay, my origin is here. That means my x position is 0, and then y is 0. But maybe there's some obstacle over here, and it's, maybe from here to here is like 12 meters apart, and maybe this is Maybe this is like 6 meters high. Just like sketch out the problem, right? Sketch out the problem and then write down all the things that you know about all the different velocities and accelerations and their positions. Just try to just write it all out. So that's like step one. Or step two. Step one is read the problem. Step two, what I do is let's just like sketch it out. Then once you sketch it out, then you need to like draw graphs for each object and for each thing that you're looking for. So let's say we have a dog and a cat, right? So there's a dog and a cat, right? And those are the things that are moving in this scenario. Obviously, you could have a baseball or just a generic ball or whatever, a brick, whatever the objects are that are moving. So you want to like find out what are the different objects that I have and how are they moving, right? So, for example, here in this dog and cat, maybe here in the middle I'll do a ball as well too if I have enough space. And so hold on, let me change my color. So I would be like, okay, so here's the dog. So I need like my velocity versus time, maybe acceleration versus time. Maybe I want my position. Maybe I'll use R for position. Position versus time. And then same for a ball. I want my velocity versus time, my position versus time, and maybe the same thing for the cat too. Velocity versus time, position versus time, versus time. But let's imagine these objects are moving in a plane, right? So it's like an XY plane. So then you may want to say, okay, well this is in X. This is an X, this is an X, this is an X, this is an X. And then you would want to obviously do the same thing for Y too. You'd want to say the velocity in Y, the position in Y, the velocity in Y, the R for position in Y, right? So you'd want to do that. This is my Y, this is my Y. So you have to create your graphs, right? And then after your graphs are here, you're like, okay, and then you have to figure out, what does this look like? 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 And then how do you figure out what these graphs look like? Well, you can use the information that it gave you. So, okay, the gravity is pulling down, I'm this far away, my initial velocity is 3 meters per second, like whatever it is, that's going to help you create some of these graphs. So let's say I have, let me erase this part right here. Let's say I had my velocity graph, okay, on the dog. So say I'm right here, and I already, based on the information given to me, I already have my velocity in X for the dog. I already know what it is. And what I want to do is I want to find my position in X. Well, what I want to do is integrate. I want to integrate that function from the velocity in X to find my position in X, right? So after you've integrated it now, but if you integrate, you're gonna have to figure out what is the initial condition, and maybe the problem will tell you the initial condition, but the mathematics is not going to tell you the initial condition. You're gonna have to know that. So once you integrate, and then plus if you have the IC or the initial condition, then you can create your graph like that. Also, let's imagine down here. Let me just change it to maybe this color. Let's imagine I had my position in Y. Let's imagine that was given, but I didn't have my velocity, right? So then I could go here, and I can go from here to here using the derivative, right? d dt of this function, and then I can create another function. Maybe it's like that or whatever. Okay. So if I'm going, I like to call this as like going down. So imagine you have like a graph here. This is my acceleration graph. This is my velocity graph, and this is my position graph. If you're moving in this direction like this, you're integrating, right? I'm integrating. So to go from acceleration to velocity, you're going to integrate. But once again, you're going to need, once you do go from acceleration to velocity, and you've integrated, that's great. But then you're going to have to know what is the initial velocity. You're going to have to know. Maybe the problem will state it, but you're going to need that. And if you're going from velocity, let's say, to position, you're also going to have to integrate from there as well too. And then once again, you'll have to know the initial position. Conversely, if you go in the opposite directions, let's say I go from here to here, or from here to here, right? Then you're just going to differentiate. And then in that case, you don't need the initial conditions because all the information is actually inside the formula already. It's already in here. So once you differentiate and you become here, all the information is already there. So you're good to go. The problem is that when you're integrating, you lose information. Well, let me say it like this. When you're I like to call this like the bottom. And then this is the top. So the bottom has like your the position, and the velocity is like in the middle, and then acceleration's on the top. When you're at the bottom, you have all the information you need. And so as you go up, you're losing a little bit more information, and you're losing a little bit more information. So by the time you're at the top, you've lost a lot of information. So that's why when you go back down, you need to get more information. And how do you get that? Well, you have to. That's your initial conditions. Okay. So that's basically it. So you need to obviously read the problem, sketch it out, draw your different graphs, and then you're like, well, how am I going to draw the different graphs? Well, the problem will tell you some of it, but then you're going to have to use algebra, trigonometry, and or derivatives, or integration to like figure out how to actually create all these graphs. And then once you have that, then the problem may be like, let's say let's say you're looking right here and you're like, oh, I just want to know what's the value here. Well, then you just plug in t in your formula and you'll get the value. So in that case there, you just plug in on the x-axis, and you'll be given, for example, your for time, and you'll be given the position in y, which is cool. Other times you may have like, a function that looks like this, and then maybe there's another function that looks like, I don't know, like this or something like that. And you want to know where do they intersect? Where do they intersect, which is right here. And so let's call this one function 1, this guy is function 2. Then you would just say where does function 1 equal function 2? Okay? And then obviously, function 1 is like, I don't know, x squared plus 3x, equals, and then function 2 is, 9x plus 3x, or whatever it is. And you're going to have to figure out where, like, what the value is. So when you find out what x is, in this case here, it's where do they intersect? Okay. Normally it's t. Normally you're looking for time. So at what time do these functions intersect? And maybe it's like here at 3. So like at time, for example, 3 seconds. So at 3 seconds, these two functions intersect, and maybe that's what you're looking for. Or you could have a lot of functions, right? You could have like this. You could have this function, and you could have this function, and you could have, like, I don't know if you can actually do that or not, but something like that. You could have 3 functions, and you want to know like where do all 3 of them meet, right? And so you want to know where does function 1 equal function 2 equal function 3, okay? And so that's like a system of equations, and that's basically it. So once again, you don't have to use the formulas given in the book. You can just read the problem, sketch it out, write down all of your motion graphs, like acceleration, velocity, position versus time, using, like I said, algebra, trigonometry, integral or differential calculus. Then once that's done, then you just you can kind of like set the functions equal to themselves, or solve a system of equations, or plug in your independent value to find the dependent value. But that's it. So once you do this, it's more, I don't know, I think like gratifying in a way, because instead of someone giving you like, oh, here's an equation, you can just solve it more graphically and or analytically, and it helps you, for example, me, like understand actually what's happening from a mathematical perspective than someone just essentially giving me the answer. All right, so that's part 1. Next, I'm going to be talking about part 2, like how to solve these motion problems, but more complicated problems. And then I'll be talking about how to solve, summarizing how to solve relative velocity problems. Okay, so I'm going to continue on. In this section, what I'm going to talk about is solving more complicated motion problems. So just to show you what I mean, let's imagine someone just throws a baseball, right? So let's say you have a nice velocity versus time, and let's imagine this is our velocity in y, okay? And let's say the initial velocity is 3 meters per second. Great. And the person throws it, and the ball goes like this, and then due to gravity it slows down, and then eventually boom, and hits the ground right here. Well, this is easy. This is an easy problem because what actually happened is it started out with an initial velocity of something, say 3 meters per second, and then gravity came in and it changed it. It affected its course, but that was it. And so you end up with just a nice parabola. Now, let me sort of sketch this a different way. So let's imagine you said this. Let's imagine it was 3 meters per second. So it was 3 meters per second. This is still velocity and time. Okay. So what you could do is you could say, all right, I'm just going to take the 3 meters per second, which is my initial velocity, and I'm just going to draw a straight line, meaning it doesn't change. It's constant. Okay. Now, of course, it's not constant, and the reason you know that is because gravity, of course, this is in y, is that gravity is going to affect it. But what you could do is you could just create two functions. One, this function is just called 3, right? And the velocity as a function of time is 3. So that doesn't matter what t you put in there, you're always going to get 3 out. Okay, so that's this line. And then you could create another line that was just gravity. So gravity is 9.8 meters per second squared. And so let's say you did something like this here. And so that would be negative 9.8 t. So that's that. That's what that line looks like, negative 9.8 t. Okay, and that is due to gravity. So the black one over here is my initial condition, if you will, and this red one is gravity. So I had my initial condition, and then gravity came in, and it started affecting the ball, right? So what's going to happen is you say, well, I have two straight lines. How does this become how does this become a ballistic trajectory? It's because you have to add the functions together, right? Once you add this function and this function, once you add those two functions together, then the composite function is correct. And the composite function is correct, which is, as you might imagine, it's just the two functions added together. So your final velocity as a function of time is negative 9.8 t, that the red function, plus 3, which is your initial condition. So I took basically two straight lines, one that's horizontal, one that's diagonal, and then I ended up creating something that is a combination of those. Okay, it's a combination of those guys. Then once you had that, your velocity as a function of time, then you could create your position r as a function of time by just integrating, right? You just integrate this guy, that's negative 4.9 t squared. Just take half of 9.8, and then you put an extra power on t, and then plus 3t. And then, but of course, you're missing your initial condition, right? You're missing your initial condition right here. You'd have to find out what it is, read the problem or whatever. But you're gonna have to figure that out and go, oh, it's actually 9. It's 9, or whatever it may be. But the point of showing you this is that this is how this works. It's actually, you have your initial condition 3, which is a straight line, a straight horizontal line, and then you have gravity, which is something else, and that's going down at a negative 9.8 t slope. And then you basically just put those two functions together, and that creates your aggregate function, which is this. And then once you have your aggregate function, then you can integrate it. You can integrate it and create this function plus your initial condition. Okay. Now, but the complicated thing occurs is that what happens if someone at 3 meters per second, it's the same problem, velocity and y with respect to time. And let's imagine this happened, okay? And then let's say that the gravity came in. So just like normal, gravity comes in, and let's say it starts here, right? As soon as you start throwing the ball here, okay? So this one, this function is just 3, and this function here is, the red one is negative 9.8 t, which is great. Okay, that's what I just did. But let's imagine something else happened. Let's imagine at time, let's say here, let's call this t1. Okay. Let's imagine there was a booster rocket, some sort of engine on the baseball, and it caused it to accelerate up at like a positive slope. So right here, you'd say like, okay, well, I have some function here. Whoops. And let's call this, I don't know, 5t, positive 5t. Okay. So this is, let's say at time t1, oh, actually I should be here. I'm down here at the bottom. At time t1, capital T1, some engine on the baseball kicked in. Well, so we still have the function 3, which is his initial position, his initial velocity, and then we have the red arrow, which is the gravity pulling him down to negative 9.8, which started at time 0, right? Because this is 0 right there, right? So as soon as you let go of the ball, gravity is going to start going. But let's imagine at t1 seconds later, some engine came on. Okay, so would you actually draw the graph look like that? No, if you had 5t would look like this. It would look like this, right? So, but if you wanted this one over here, it would be 5t minus t1. Okay, so when you say minus like something, so minus causes, or subtraction causes the graph to move to the right. If it was positive, it would move it to the left. Okay, so 5t minus t1 causes this function to go right here. And then let's also imagine at time t2, let's imagine there was like another rocket engine. I don't know, just because I'm running out of ideas. Let's imagine there was some other rocket engine going at 8t. Okay. So that's the slope there. And once again, if you wanted this graph to actually be here, you'd have to say 8t minus t2. Okay. So now as the ball is moving, so initially between 0 and t1, just gravity is affecting him. But then between t1 and t2, he has gravity and this we'll call it the green force. The green force is affecting him. And then after T2, he has gravity and the green force and now the blue force. They're all affecting him, okay? And so you can put those three functions together. You could say like, okay, well I have so my velocity as a function of velocity in y as a function of t is actually my initial velocity 3 minus 9.8 t, which is gravity, and then you could say plus 5 t minus t1, which is the green force, whatever that may be, and then plus 8 times t minus t2. Okay. And then there you go. And then there's your velocity as a function of time for this more complicated scenario where there's multiple forces attacking the baseball along his flight path at different times. Okay, and then once again, if you wanted to okay, well, I needed to, I want to find my position in y as a function of time. Now it's easy. Now all you have to do is just integrate this to find the other one. 3 becomes 3t. This becomes negative 4.9t squared, plus this becomes 5t minus t1 times t, and this becomes, because basically this is a this is like a constant, and then plus 8 times t minus t2 t, something like that. Okay, and so this is what happens when you integrate from here to here. Now obviously after you do that, you're also going to have to say plus you need your initial condition, which is not going to be in the velocity, right? So once you integrate down, you're going to have to find out what your IC is. Now, here's the problem with this. So I want to be very clear about this. Any times between 0 and T2 are now corrupted. So if you're like, oh, I want to find out, I want to plug in my function either the velocity or the position, I would like to pass in, this time or this time or this time or this time or this time, and have it tell me what happened. You can't do that, because these functions are, what's happening is for example on the blue one, the blue one is going up, but he's also going backwards in time. You see that? And they're just like the green one. The green one is correct in this way, but he's also going backwards in time. So it's affecting, and I don't want that, right? I want it to start there. I want the blue one, for example, to start at T2, but you can see the tail actually goes backwards into the yellow area. I don't want that to happen. Same thing with a green one. Yeah, this looks great, but when you start going back, that's going to mess up your previous data. So because it does that, your data between 0 and T2 ends up being corrupted or bad or dirty, or however you want to say it. So you can only actually use this data starting at T2 and going forward. Okay, so as long as whatever you're looking for is starting at T2 and onward, great. But if you're looking for something between 0 and T2, no, your data has now been corrupted. So just something to be aware of. All right. Anyway, that's it. I just wanted to go over how to solve a more complicated motion problems by essentially combining functions together. And that's it. And then next, I'm going to be talking about relative velocity. Okay, in my final and third section, I'm talking about or summarizing relative velocity. So as I mentioned, I've already done some examples on relative velocity. You can just watch those on the YouTube. I'm just going to go over, like I said, a summary. The first thing I want to talk about is, what is relative velocity? When you talk about relative, what does that mean? Well, let's imagine I have a person. I want to know what the velocity is of a person relative to the Earth. What does that mean? Let's imagine you put a stake in the Earth right here. Okay, so that's the origin. And as this person, let's say, is running in this direction, this arrow is relative to the origin, Earth, right? So the Earth here is that. It's relative to that. So as this person runs around or whatever, it's relative to that point. So as a person moves farther and farther and farther away, it's still relative to this initial point, okay? And it can be any type of the Earth where it could be like dirt, it could be like a tennis court or a football field or whatever, but it's just like some patch of ground that's not moving, right? So that's pretty simple. So again, just to recap, when you say the velocity of a person relative to Earth is the thing on the bottom, imagine putting a stake in it, okay? Now, it gets a little bit trickier is if you imagine something that's moving. You say, let's imagine a boat relative to water. So these are the shores. Let's imagine the water is in here like this, all right? Let's imagine the water is flowing in this direction. let's imagine the water is flowing in this direction. Of course, it's flowing in that direction relative to Earth, right? The Earth is like static here, and let me just go back and change that color. So you can imagine putting a marker down here, and you can see, yeah, that this water is moving in reference to that reference point. But let's talk about, like, for example, like a boat. So imagine you put a boat in here. All right, here's a boat. And you want to know its velocity relative to water. Well, what does that mean? Because the water's moving around. What I like to do is imagine like picking a piece of water out, like a molecule or something right there. There it is. And you're compared to that. So remember, this is because this is what you're comparing it against. That this is now your origin. Okay. So the boat then is here, right? So it's that arrow relative to the origin. But what happens is as this thing moves, right? Let's say it's down here now because it's the water is moving in that direction. The water is moving to the east, let's say. And let's say the boat keeps moving. So now the boat's over here like that. So it looks like the velocity of the boat is really fast, right? It looks like the velocity of the boat, because look at it now. Look how long that arrow is. Well, it's only longer because, yeah, the boat is moving upstream at some velocity, but its reference point is also moving downstream. So those are like adding together, which is making the overall velocity vector look longer, okay? So anyway, the point here is that when you say, say a boat relative to the water, or an airplane relative to the air, imagine picking out a little bitty molecule and seeing what's happening with that molecule. Is it moving? Oh yeah, so this thing is moving in this direction, whereas the boat is moving in this direction. Therefore, the resulting vector is going to get longer and longer and longer and longer. So yeah, so that's just something to remember, is that, yeah, sometimes you're gonna, if it's relative to the Earth, yeah, just put a stake down. But if it's relative to some fluid, let's say, that's moving around, like a water, a liquid, or a gas, imagine just picking out a little molecule of that and seeing where that thing is moving. Because wherever that moves, that's your origin. So your origin is moving. Okay, so there's that piece. The other piece that I want to talk about is reversing these arrows. So let's imagine I had the velocity of a person relative to Earth. So let's say this is my origin here, like this, and let's imagine I had a person that was running with this velocity like this. Okay, so he's running due north. That's the direction, and let's say he was running at 5 meters per second. So that's the magnitude. The direction is north. Great. So that's the velocity of the person relative to Earth. So the Earth is, we have a stake in the ground. That's our origin. And then the person is running away from that origin. But imagine you wanted to flip the arrow. You want to flip it. Meaning I actually just want the velocity of the Earth relative to the person. Now, in this case here, you may think that's dumb. But you may, instead of saying I want the velocity of person 1 versus person 2, you may say I want the velocity of person 2 versus person 1. Okay, so you may want to flip that. So how do you flip this this relationship? So what you do then is you say, so now it's the person, right? So imagine this is the Earth right here, and this is the person. This is the person. So now the person becomes the origin. Now the person becomes the origin. Okay. Now you might be thinking to yourself, yeah, but the Earth isn't moving, right? Yeah, but the person is moving. So let's imagine the Earth is here. The Earth is E. Okay, he's still not moving, but the person is moving. So let's imagine that the person is moving, here now. So let's imagine the person is here. So the vector initially looked like this. Now it looks like this. Now it looks like this. Because the origin is now the person. The origin used to be the Earth. Now it's not. Now it's the person. So as the person moves around, that's now the origin. Okay, that's now the origin. Now, a quick way a quick way to reverse these arrows is just reverse the vector. So in here, when I had the velocity of the person relative to Earth, you could just simply flip it around. So at any time it's like, oh, I just want to flip it. So instead of looking like this, you could have it look like this. So it's still 5 meters per second. It's still the same magnitude. It's just the direction is the opposite. So that's all you have to do is just essentially flip the arrow wherever it's pointing, and that's now pointing the opposite direction. But keep the magnitude. Now you may be thinking, yeah, but isn't it +5 and isn't it -5 here? No, that's just this. 5 is the speed, and so speed is always positive. The direction can be anywhere at once, but the speed itself is actually just the magnitude, which is 5. Okay, the last thing I want to talk about is how to solve one of these problems, how to solve a relative velocity problem. So you read the problem, sort of sketch it out, and then what I like to do is draw all the objects on your screen. So let's imagine there's a soccer match, and there's a player 1 that's playing, and there's a player 2 that's playing the soccer match, and then there's a ball, and let's also imagine that there's the Earth. Okay, there's the Earth. And you would like to know like different velocities, like P1 versus P2, the ball versus the Earth versus P2. Okay, you like to know some different things. Okay, so maybe the initial sketch is, what I'd like to do is I'd like to find out the velocity of P1 relative to the ball. Okay, I don't know this. I'm going to put a question mark here, meaning I don't know what it is. But I do know that the velocity of P2 relative to the ball, I do know that one. And I do know the velocity of P2 versus the Earth. I do know that. And I know here, this is the velocity of P1 versus the Earth. So let me talk about this for a second. Like, how do I know the arrows? So when you say, for example, and I'll end up just erasing this, velocity P2 versus the Earth, or relative to the Earth. You start at P2, that's where the arrow starts, and you follow it to the Earth. Okay, you follow it to the Earth. So when you say P2 relative to Earth, you start at the P2. Think of this as the numerator and denominator. Start at the numerator and move to the denominator. Okay, so and over here, the velocity of P1 versus the Earth. You start at P1 and you move to the Earth, and so that arrow is pointing from, for example, P1 to E. It's pointing in that direction. That's actually very important. Okay, I'm going to go back in time and remove some of these things. Great. So what I'd like to do is I would like to find out this. What is the velocity of player 1 relative to the ball? Okay, I don't know what it is. But before I do that, so in these other ones, let's say I know what the actual velocity looks like. So let's imagine over here, it looks like the velocity vector looks like that. Maybe it's 3. And over here, it looks like this, and it's 2. And then over here, let's imagine the velocity vector looks like this. It's pointing down at an angle. Maybe this is 7, okay? And those are in meters per second. So I have all those vectors. But I don't actually have this thing in yellow, the velocity of P1 relative to B. So how could you do that? How can you get from P1 to B? So imagine you're walking that. See the arrow? The arrow starts at P1 and it goes to B. Is there another way to go on a trip, let's say, from P1 to B? Yes. You could go, P1 can go here. It's sort of stuck here, and then you could go here, right? The problem is going from E to P2 doesn't work. So what you'd want to do, because the arrow is in the wrong direction, what you could do is just flip it around. Create a new arrow. In order to do that, is you'd say, well, I actually want the velocity of the Earth relative to P2. I don't want P2 versus the Earth. I want the Earth relative to P2. And so if you did that, you'd have to take this vector right here and flip it around. So it would look like this and look like this, and you'd flip it around, okay? And so now I have this path. So as you can see, I can go from P1 to E to Earth, and now I can go from Earth to P2, and I can go from P2 to B. So instead of going from P1 to B directly, I'm going from P1 to E to P2 to B, okay? And this actually works out. So I'm going to do a little a formula. So if I say the velocity of P1 relative to the ball, that's what I'm looking for, that's the yellow, is equal to the velocity of P1 relative to Earth plus the velocity of Earth relative to P2 plus the velocity of P2 relative to the ball. And then what you could do is you could imagine like this is the on the denominator, that's the numerator, denominator, numerator. And so what you're left with is P1 versus B, or P1 relative to B, P1, B. That's the only thing that's left. You essentially canceled out everything else, okay? And so once you did that, you would then have that vector. So whatever this, whatever this, I don't know what this vector looks like. Whatever, it may not point in this actual direction. Maybe this is 7.3 or something. So once you've added those, the P1 relative to Earth, the Earth relative to P2, and the P2 relative to B, once you've added those three vectors together, you'll get your new vector, which is P1 relative to the ball. And so this is how you can solve rather quickly a relative velocity problem.